Right, so yesterday we looked at taking Lewis structures and then working out from the Lewis structure what the shape of something might be, and we used marshmallows and toothpicks to represent atoms and bonds and lone pairs of electrons respectively. So what we are going to do is go, how do we justify or explain the shapes of molecules, and how do we draw them on a two-dimensional structure like a board when they're actually three-dimensional shapes? So we've got a few things we have to consider. First of all, we're always focused on the central atom. We always look at the central atom first. And around the central atom, we ask ourselves a couple of questions. Question number one is, how many regions of electron density? What does that mean? Well, the regions of electron density mean it's a lone pair of electrons. That would be considered one region of electron density. So it is a lone pair of electrons, or it is a covalent bond or a chemical bond. Now, to clarify, a single bond is one region of electron density. A double bond is also considered one region of electron density. So if I had something like methanol, and here's its Lewis structure, it has got two single bonds and one double bond. This has still only got three regions of electron density. So even though it's a double bond, we don't consider it to be two, it's just one. So that's my first question I ask. Then when I'm looking at working out my shapes, I need to ask how many atoms are bound to the central atom. So because that's going to determine my shape as well. And we did a table that I photographed yesterday where we had regions of electron density for lone pairs might have been 3, chemical bonds was 1, and so our shape was linear. So that's how we construct that. I'm not going to draw that table up again, but I'm going to use it to show you how we explain the shapes and then how we draw them. So the first one I'm going to look at is 4 regions of electron density. And how we draw this. So if I've got my central atom, I'm just going to use a circle for this one. You'd use the symbol, so carbon, for example, that's probably our most common one, would go in the middle. To show this in 3 dimensions, whatever atom that might be, we have one region of electron density that goes straight up. We have to estimate 109.5 degrees because that will be our bond angle for these. Whenever there's 4 regions of electron density, it's about 109.5 degrees. It doesn't matter if you get it slightly wrong, but if you go into thirds and then just go a little bit higher than that, you're right. There's going to be another chemical bond on the same plane, so we can use a line for that. There's also going to be one that goes basically straight into the board. Well, that's pretty hard for me to draw. So one that goes straight into a bit of paper. So we use a dashed line that gets smaller and smaller and smaller to give us the optical illusion that it's disappearing into the board. And then out here, there'll be one sticking out here, but it will be coming out of the board at us. So it'll come out to us. So we create a triangle that gets bigger and bigger and bigger, so it's getting wider to show the illusion, as it were, of that coming out of the board at us. And that's how I show 3 regions of electron density. The angle between these will be 109.5. Now in year 13 we refine that because of the repulsion of lone pairs being a lot more. But because these are regions of electron density that are all negative, they repel each other. So to get as far away from each other as they can, the bond angle is 109.5 for all of these. We call this electron cloud shape tetrahedral, but it doesn't mean that every compound with four regions of electron density will have a tetrahedral shape. Water is a good example. It has four, but it's a bent shape. So now I know something's got four regions. I know its bond angle is 109.5. It has got a tetrahedral electron cloud. Then I go, how many atoms is bound to it? And this is where that table from yesterday comes in. If there are four things bound to it, it is a tetrahedron, or tetrahedral for shape. If there are three, the shape of the electron cloud stays the same. It's still got a tetrahedral electron cloud. But if I have an atom here, here, and here, and a lone pair of electrons here, then that's pushing those down to make my trigonal pyramid. So triangle-based pyramid. If I have got only two of them, so one of these other ones is also a lone pair of electrons, like water, now hopefully we can see why that's a bent shape, not linear. So once we've got our region of electron density, we then look at how many atoms, and that tells us our shape. For three regions, which is the only other one that's a bit tricky, because it's got a couple of shapes. For these ones, we can draw these very easily on a page because the best way to spread three electron clouds or regions of electron density out in three-dimensional space so that they're as far away from each other as possible is that they are the corners or apexes of an equilateral triangle. So they sit on a board. So this is going to mean one of these is going to be a double bond, almost certainly. So for this one, our bond angle is going to be 120 degrees because it has got a trigonal planar electron cloud. So therefore the shape, if I had atoms on all of them, would be trigonal planar, as we talked about yesterday. But again, this would justify why if I had two atoms joined to it, this would have to be a lone pair of electrons. Why it is a bent shape, not linear. When you're explaining the shapes of things, you have to discuss the electron cloud and then the number of atoms that central atom is bound to, and that is how you justify your shape.